Hello friends, welcome to today's session. Today we're going to discuss about the vector auto regression model. So we have discussed about the auto regression models. So in simple terms, like is time series data at any given point of time t is dependent on its lagged values as well, like t minus 1, t minus 2, t minus 3, how many lags that will determined by some methods. But this is like overall idea of like the auto regression model. But what is the vector auto regression model and where it is used? So today we will discuss in this session like in which kind of data set the vector auto regression model is applied, what is the vector auto regression model and what is the basic idea behind it, how can you check that this data set is fit for VATOG or vector auto regression model using like the Johansen test or the Granger test. And then like we know like the simple methodology how to check the stationarity or the seasonality of a time series data using the AD Fuller test. Then we will fit the data set into the model, the VAR model. And then, by the way, vector auto regression is also called a VAR model. And then, like, we'll check how many lags we need to, what is the p value, what is the number of lags value to be put for that fitting of the model for the data set. And then we'll predict, or rather say forecast the data for the to compare it with the test data, and then we'll plot it side by side. So this is like the whole journey today we'll cover. So this video will be somewhat long because we will cover both the theoretical as well as the practical. Please stay tuned. Let's start. So if I say about the what is vector auto regression model, so that means like there are two time series you can say which are interdependent, or in other words you can say like if these are the two time series data like a and b, a causes b as well as b causes a. It's not like that there are two features in a data set, like you can say that holiday effect on the number of visitor in a restaurant. Okay, so in that case holiday causes the number of visitor, but there is no the vice versa relationship, right? But if you can say uh, there are two values like cost of the apple and cost of the banana, like two fruits, or you can say like the best example, because this vector auto regression model has very much application in the the stock market world. So you can say the stock exchange of America is somehow dependent on the stock value in UK, right? And like this APAC country or the European country or the American country, these three are interdependent. So one in one stock exchange, what is the stock value can cause the other stock exchange value. So in one word, I say if A, so this is like rather than before A, so I can say like it is Y. Okay, so Y1 and Y2, these are the two stock exchange stock price. Okay, at some given point of time T. Okay, so in auto regression model, what I can say, like there is a constant factor like alpha 1, and then there is like beta 1 and y t minus 1 and like t minus 2, t minus 3. Let's say in this case, it is only one lag dependent. And then there is some error factor, right? So this is whole and soul the auto regression model equation, and same for y2 y2 as well. But if I say that these two can influence each other, or they are the co-integrated, or they can cause each other. So in that case, I will write the same equation like y1 t, y1 at some point t is equal to alpha 1, the constant factor, and then beta 1 1 y1 t minus 1, and then beta 1 2 of y2 of t minus 1. Okay, so that is dependent on y2 as well. So this is the differentiating factor between the vector autoregression model and the autoregression model, and there is the error part always. And same case, y2t is also dependent on y1. So that is interdependent. Like this is alpha 2, and then beta 2 1, y1 t minus 1, and beta 2 2 y2 t minus 1. Okay, and the error part. So if this is the time series dependency, then we need to apply the vector autoregression model, and this is the time series function, you can say. Okay, so first thing we will say, we'll take two time series data that will assume that they can be correlated or co-integrated, you can say. So I will take two time series. One is the money stock, another is the personal spending. Okay, I assume that these two are co-integrated to each other. So I just read this data set, and I got this data from Kaggle. I will give the link in the description. You can use this data creating an account in Kaggle. So first thing first, so when I read this data, I will make sure that I will parse date, because the date should not be read as string. Date should be read as date, as like date. So this is a monthly data, and this is like, you can say it's some money value, money in stock value in dollar or a billion of dollar or million of dollar, whatever you assume. But I will say that this money stock and the personal spending both are in the same granularity, like they are monthly data. And I'll make sure the date column is my index column. Okay, so next thing is the personal spending. I'll apply the same logic here as well. The index column is the date column, and I will parse date as date. Now I will join these two data set to create my data set to go forward. So now we have the money in stock and the personal spending in the same data set, and the date, the monthly data, is my index. Okay, the first thing, before doing anything, I will plot the data set to check what's the, you can decompose it to check the trend, seasonality, and the randomness side by side, or you can plot it. So I just plot this data as it is, using some subplot. So you see there are two columns, right? So the number of columns is equal to 2, because this is the this is taken from this data set, and the number of columns, and this is 1 means there will be only one column. I will not create a matrix. I will create one graph for each row, and index means this is my first column and this is my second column, and I will create these two subplot. So mostly you can see there is lack of seasonality, but there is always a positive trend of this data set for the money in stock as well as the personal spending. So these two are more or less same. Now I will do the test where I can check that this data set is fit for the vector autoregression model or not? Can I use the vector autoregression to predict the future for this time series data? So to do that, I will use the Granger causality. Like if A causes B and if B causes A, then I would say that this data is fit for VAR model. So I imported the Granger causality test from the TSS stats tool of the stats model, and I have the max lag as 10. What should I check for? So this is very important. Please concentrate so that this is like a very important 5 minutes in this video. First thing, what I should check. So there are 4 kind of parameters. Please concentrate on any one of it for this causality analysis. So I will take the SSR based chi-square test. Okay, you can check for any other. But what you need to do, you need to go for the p-value and check what is your minimum p-value in this number of lags. So in this 10 lags, what is your minimum p-value? So I just check for like how spending causes money. Okay, so if spending is my x and if money is my y, so how this is causing, x is causing y, or spending causing money. Okay, so I will check for this p-value. So p is 0.4195 and rather it is decreasing and decreasing further. And it is again increasing, it again decreased. Just check. I think this is the minimum value because it is 0.0018. So I think this is the minimum value. Okay, for like spending causes money, p-value is 0.0016. Now this is a null hypothesis testing. So you can rather reject the null hypothesis or you can accept the null hypothesis. So our null hypothesis is like this is not causing each other if the confidence is 5%. Now P is 0.0016. It is less than 0.05. What is the confidence score I would assume? So then I would say I can reject the null hypothesis and accept spending causes money. Let's check for the other one. Now, money causes spending or not. So I'll check for the same chi-square test and I will check what is the value. So it is like p.51, 0.51, 0.15, 0.17, 0.18, 0.14, 0.07, 0.11, 0.04, and 0.12. Right. So at last, it is having a very good p-value where I can reject the null hypothesis and accept the money is causing the spending. So can you say, is this data fit for VAR model? Yes, because money causes spending and spending causes money. So in both cases, we can reject the null hypothesis and accept the causality. So here P is 0.012 0. Okay. Now let's proceed. There is another test for this, like causality testing, or you can say co-integration testing. So that is co-integration testing, rather you can say the causality testing. So that is the Johansen test. So what is tested there? So there are two things tested there. One is that what is your trace analysis, okay? And for input, you need to pass the data set, and you need to give that what is your deterministic order. So what is the, like, how the time series data is, like whether it is deterministic, or it is having a linear trend, or it is non-deterministic. Okay, so anything based on the graph plot or based on the time series data analysis you can choose for. And the second thing is what is your, like, the lag difference. Okay, so I will discuss about this lag difference later. Now you can just assume that I have taken the lag difference as 4. Okay, and I would say this deterministic order of this time series is non-deterministic, like -1. So based on these two value, I just check what is my trace value for both the feature or both the columns, and then what is its critical values, like at 90%, 95%, and 99% interval. Okay, and whether it is less than or greater than. In this case, this is just opposite. If this trace value is greater than critical value at some like 95% interval, okay, I would say, then I will reject the null hypothesis and assume the data is co-integrated. So you can say like 27 is very much bigger number than these all values, like any critical value, like at 90% interval or at 95% or at 99%, anything 27 is greater than. So you can easily reject the null hypothesis in case of money. Okay, and say that money is co-integrated with the spending, but it is failing for spending. The spending is less than, the trace value of spending is less than the critical value at, like, say 95% interval or 90% interval or 99% interval. So this is not co-integrated. So you can check this test. I assume by the Granger test, I assume that this data is like correlated. So I'll proceed further. Okay, but these two tests is very critical to check whether you would apply the vector auto regression or not. Okay, let's proceed. Now the, like, usual test, like Eddy Fuller test for the stationarity checking. So I will just check the what is my Mackinnon's p-value, and if the p-value is less than 0.05, I will say the data is stationary. Otherwise, I will say the data is seasonal or having some trend part or the seasonality part in this. So let's run this. So for both money as well as the spending, the p-value cannot reject the null hypothesis. So what I say, I will say the difference, I will create the lag difference to get the, like, to remove the trend part from the data. So any data is having a trend part as well as the constant part. So if you difference this data from itself, so it will actually remove the trend part out of this data. So this is very usual. I have explained it in my previous video. You can check it. So what I would say I would do, I would just go for dataset dot diff So this is the like simplest way of doing it. There are many other ways to do it. And I will check the stationarity again. So I will say that for money, it is not stationary, but for spending, it is. So I need to differentiate it again. So I just do the both time differentiation, and then like this is the first time, one time, what I have checked. This is not creating the indicating the stationarity for both the feature. That's why I have done the double difference. Okay, this is the first time first order difference. This is the second order difference. Okay, and then I will check the value. So you can see the data is not stationary for both the feature because it is less than 0.05, the confidence p-value. Okay, you can reject the null hypothesis for both the features and accept the data is stationary now. So I will rather say like let's keep this part because if you like take the first order or second order difference, you need to reverse it as well. So I'll just keep it. Okay, I'll just check take like go ahead with the data whether it's stationary or not. Okay, so I'll use the original data itself and let's see what happened, how much clear we have. Okay. So for like very small data set, it's okay. So now I'll do a 90% and 10% train and test split for my data. Okay. So 90% data is my train data and 10% data is my test data. Okay. So now you need to fit the model. So there is a very good and smart function like select order. Okay, you can use to determine how much lag you need to provide to fit the model and predict the future. Okay, so this is the select order function. Okay, and you can check with any number of max lag. The beauty of this method is it will give you like what you need to check. You need to check the Akike information criteria or Bayesian information criteria or any of these four values like AIC, BIC, FPE or HQIC score. What you need to check in which lag you are getting the minimum AIC score or minimum BIC score. Okay, I'll go with the AIC score, and the beauty is it will give you with a star what is the minimums. You just no need to search for it. Okay, so this is for AIC, this is for BIC, this is for FPE, and this is for HQIC. So I'll go with AIC. So my lag is 5. Now I have said like I will discuss it for like later how you can take the k-diff value, okay, the number of lag difference in case of Granger test, not in case of Johansen test, the co-integration test. So in that case, this kr difference is equal to the lag you have determined using the select order minus 1. So this is like how they have defined it in their example and in their the documentation. So kr difference plus 1 is equal to the k where the var is fitted. Okay, that's why I have taken 4 there. Okay, now I have using the AIC, I have taken the lag is equal to 5, and then I will fit the model with this lag 5. Now I need to forecast. So the function is forecast, not prediction. So this is the function you need to use. And what are the parameters you need to provide? First parameter is This is the lags. Okay, so lag order you need to give up, provide, and this is the number of observation. Like if you want to predict and compare with the test data, the number of observation will be the same as number of index in your test data. Okay, so I have just taken like that. So I have taken the length of the test, and that will be my number of observation, and that I have provided in my steps. So that will be number of observations in test, because I want to compare it side by side. And this is my lag order. Okay, what is my lag? So that is p is equal to 5. So I have taken the last 5 value from my train. So that is like just before the test value starting. So that is my lag order for my test value to start. That's why I have given y is equal to forecast input, and forecast input is equal to taken that from the train value, the last 5. Okay. So these are the two parameters you need to give. And then once it is giving you, so this is just like a multi-dimensional array, and you need to like change it to a data frame, and you just can use the index of test and the column of test, because this is same, like you just forecasted the same thing, and the number of observations are same. That's why you can use the same index, and number of columns are also same. That's why you can use the same columns. Okay, and now you can forecast. So these are the forecast value. I'll just not see it. You can just take the root mean square value, or you can like plot it. So I will like plotting is like more attractive to me. So I just plot it is side by side, and for both the features, and check like whether it is forecasting properly or not. So it's say like the forecast in orange and the actual test data in blue, they are actually almost in the same line, right? There are some difference, but like you can say that your prediction is as good as the test data is, the actual data is. So this is good for money, and this is good for spending as well. So that's how, and you can just check the root mean square value as well for both money and spending. So in that way, if the data is co-integrated, so there you can use the vector auto regression. So if you think this, you can have this kind of valuable input in machine learning, and you can like just have, you can just request your uh, area of study, and you want to have some example, you want to see some video to help yourself, just like hit the like button. This will like encourage us to provide you with the good stuff in this machine learning and AI tutorial. Thank you so much. Subscribe for more. See you soon.